So today we're going to look at 3i. We're going to talk about similar triangles, and then we're going to talk about a measuring technique called shadow sticks. So the first thing we want to talk about is we want to talk about similar triangles. Last time we were here, we talked about similar objects, similar polygons, and we said that if the angles are the same, then you know they're similar. And if their sides are proportional, then you know they're similar. But sometimes you're not going to know all the information for a triangle. And so there are certain properties that you can use to determine if two triangles are similar with knowing pieces of information. So we're going to look at 3 different properties. Now, you cannot use any more than these 3 unless there's one more extra one that's for a right angle triangle, but we're not worried about that right now. So the first one we're going to talk about is called side, side, side. And that's where all 3 sides are proportional. And remember, that means the same ratio. So what you would do is you would just define the corresponding sides and determine if the ratios are all the same. So you get 2 over 1, 2 over 1, 2 over 1. That means they're all the same. But you get 2 over 1, 2 over 1, and 3 over 1, then they're not the same. Therefore, they're not similar. Okay? All right? Well, that would be if the sides were the same, but okay. The other one is angle, 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 and that is all 3 angles are the same. And really, you only need 2 angles, because if 2 angles are the same, then what can you conclude about the third one? It has to be the same. There's no way that you could have 2 angles be the same and not have the third one be the same, right? But to keep it consistent, we look at all 3. Okay. And finally, the last one, which is the one that's most common because you have to do a little more work, is side, angle, side. Okay? That's 2 proportional sides and the angle between them. Angles between them are equal. So you have 2 sides that are proportional, meaning that if you took the ratios of them, they would come out to be exactly the same number, the same scale factor, right? And the angle between them is equal. Now, it has to be the angle between them. If it's in any other position, then this won't work, right? We don't care about the other angles, but that angle has to be between the 2 sides that you're working with. So sometimes they'll give you 2 sides and another angle, but it won't be the one between them, so you can't use this property if that's the case. Okay? All right. Now, we'll look at some examples of those in just a moment. The next thing we want to talk about is how we can use this idea of similar triangles to measure objects, the height of objects that we don't know, or the distance that we don't know the measurements of. And we can do that using shadow sticks. It's a really ancient technique. And it simply says that if 2 objects cast a shadow at the same time, okay, the triangle created, or triangles, I can't seem to do plural today. Triangles created are similar. Okay. So for example, let's say you have a tree, it's on the ground, and you have a person standing there, okay? And each one of them casts a shadow. Well, the triangle that's formed by those shadows, the object standing up, the ground obviously is the base, and then the hypotenuse is that shadow, those two triangles, if it's done at the same time, will always be similar. So if you know some of those pieces, you can use a proportion, right? One fraction equals another fraction, one ratio equals another ratio, to be able to find a missing length, okay? Because, for example, it's easy to measure someone's height, right? It's easy to take this distance as well. So you have two sides, you can finish off the triangle. It's easy to measure the distance from the shadow to the base of a tree, but it's more difficult to measure the height of a tree, right? So we could use, so this would be our unknown, the tall object. You could also do this with buildings. You could do it, the Greeks invented it so that they could measure the heights of mountains. Lots of different ways you can make this work with big objects. Okay? And we'll look at a few examples of how to make this work in just a few minutes so we can get some steps down. Okay? All right. But we're going to start first with those properties for the triangles. So let's just go to the book. So the first one, we're just going to use the rules and see which rule we could use to test it. All right? So first thing you want to do is determine, do the measurements they give you fit one of the rules? And in this, I know the lengths of all the sides. And the second triangle, I know the lengths of all the sides. Is there a property that allows you to compare when you know the lengths of all three sides? You bet. Okay? Side, side, side. And what we have to do is just take our corresponding sides and and find out if they have the same scaling factor. But if you'll notice, there's something wrong with this. The longest side of the small triangle is the base in this case, but on this one, the longest side is going that direction. So the first thing I have to do is I need to reorient that larger triangle so that the sides are the same. Now, you don't have to redraw this. Oops, sorry, that's the longest side, isn't it? It's 9 centimeters. So you don't have to completely redraw it, but if you do, you're more likely to get the pieces where you need them. Okay. So the longest side is 9 centimeters. The next longest one is 7.95 centimeters. And the shortest one is 6 centimeters. And again, you know which way to reorient it simply by looking at the measures of the sides. Longest one has to correspond to the longest one, etc. Right? Otherwise, they're automatically not similar. Okay. Now, so what I've done is it's turned it over, flipped it over, and set it on a different base. So now let's see if those sides are proportional. All right. So now I have 2.65 compared to 9. So 2, and remember it's the new one over the old one always. So the 2.65 is going to go on the bottom, the 9 on the top, and you're simply going to divide it out. And since we're only looking for the scaling factor here, you can just divide it with your calculator, and it's going to come out to be some ugly decimal. All right? Then the next biggest sides, we'll compare those. 7.95 over the 3. And then the 6 to the 2. Okay? Now, let's divide those out. So since we got the same exact scaling factor, we know that those two things are similar. Okay? Now, other properties that you're going to use. Let's see what else they do to you. So look at All right. Let's look at a couple of others. So if you look at this one, I know that one angle is 60 degrees, and the little square in the corner tells me that that is a what? Right angle. So that means that angle is 90 degrees. So they have two corresponding angles that are the same. Do I even need to know the angle at A or X to be able to tell this?
No.
Nah. If two angles are the same, that means what about all three of them? They're all the same. Therefore, by the angle property, they are similar. Get the idea?
Yeah.
All right, look at C. I know 23 degrees and 26 and 10 are the lengths. But is it? Because remember, in side angle side, where is the angle?
In between the sides.
In between them. And is this angle between the two sides that I know?
You can figure
No.
it out.
Okay.
It's 23 plus 90, which is 113 minus 180, which is 67.
There you go. So we really have two different properties that we could use here. If you think about, we already know the two angles, these two angles, then we know, if we know exactly the same angles on these and they're the same, then we could use the angle property, right? Or we could determine what this angle is by using the other two angles, and we would know the sides with the angle between them, right? But in this case, it's probably easier just to look at the angles, the fact that we know all the angles. Good eye, though. Okay? All right. Now, this next exercise goes back to looking at finding missing pieces. And if you look at these, you'll notice that the second triangle has two missing sides, right? But if I know if I know one missing side, if I can find that, then I can find the others. So all I need to do is reorient this triangle, the second triangle, to make it look like the first one. So what I'll do is just flip it over. And that gives me 10 in the bottom, and X and your Y, right? So these two sides are congruent. This is the new triangle. This is your original. So remember, it's always new over the original. So 10 over 20 gives me, okay, no, let's not do it that way. Let's do it the other way. Equals these two corresponding sides. So X over 52. Right? Remember setting up a proportion. 10 times 52 is 520, and 520 divided by 20, it's going to give me what?
26.
So that side is 26 long. Then we could do the same things using this same proportion. 10 over 20, but this time we're looking for Y. So Y over its corresponding side, which is the 48. 10 times 48 is 480. Divided by 20?
24.
So that tells me that the Y side is 24. And of course you want your units. So remember, if you don't know, if you're looking for a missing side, you just set it up as a proportion, cross multiply and divide by the one you didn't use. Right? Straight from the assignment last time. You need to show the setup, but I'm not going to be looking as much for the working. But you do have to show the setup. In this class, remember that if you don't show how you accomplished it, then you're not going to get full credit. Okay? All right. Now, all right. So we've created two triangles. Now you see why they're called shadow sticks. They stuck a stick in the ground that they knew the length of, right? Or just put it on the ground, measured its shadow, and then we also know the shadow of we have the measure of the shadow of the tree, how long that shadow is. And now we can compare those. How can we, well, first of all, they want us to know, how can we determine that these are similar triangles? Yeah, we know two of the angles, therefore it's easy to find the third. So okay, so we could use the angle, right? And I could find the measure of one of those sides by simply finding the measure of the height of the tree, setting up a proportion with the measurements that we have. Okay, and then I know the angle between them. Therefore, I could use side angle side. Okay, so two different properties would work.
8 divided by 4.
There you go. Now, find the scale factor for the side lengths of the triangle. Since I know they're similar, do I have to find... I can just find one of them, and I know that they're all the same, right? So what is the scale of the shadow of the stick?
4.
4 over what? 8?
8.
Which gives me a scale factor of 1/2.
Tree's 2 meters tall.
Okay,
1 meter times.
all right.
Well, you have to do like reverse psychology. The 1/2.
And then finding the height of the tree.
It's 2.
It's just 2 meters. Don't be working.
Yeah, I can just read it on my head.
Okay.
I don't know.
But setting it up as a proportion, because that's what we have to do, right?
Why'd you do x over 8?
Because I'm insane. 4 over 8 is equal to
X
1 over x,
Oh,
right? If we call this x.
4x. But isn't
So-
the tree the new one? You consider the new shadow?
The way we did it a while ago, it wasn't.
Okay.
Doesn't really matter. It doesn't. You're going to get the same number as long as you do the one over the other. It makes no difference. So 8 times 1 is 8. Divided by 4 gives you x equals 2 meters. Okay? You must set out the working. You don't have to show the mathematics, the work in between, but if you don't show how the process works, the proportion, then you're not going to get full credit for it. Okay? All right.